while discussing fluoride, I forgot to tell you that fluoride determination is done more than 3 to 5 million times a day all over the world because of its importance in drinking water. Now, another parameter that is of very crucial for drinking water is phenols. Now, you will come across phenols in your day to day life in several occasions. Many of the chemicals what you use for floor washing, phenyl and other things, they all contain phenols. And then in the hospitals we use Dettol. Dettol is another phenol, and phenols are contained in several natural organic substances like fruits and other food products. So, all these phenols can enter into waterways, and then many of the phenols are toxic. So, there is no need to decide which phenol is toxic, which phenol is not toxic, because under any given circumstance, the phenols can aggregate and form a concentrated solution of phenols which can become toxic. A group of phenols, what I mean is different types of phenols present in water can be quite toxic. Therefore, the government Bureau of Indian Standards prescribes a limit of 0.001 ppm of phenol in drinking water. That is, it should not be there basically, but even if it is there, it should be less than this, and provided one can drink solution containing drinking borewell water or something containing phenols up to 0.001 ppm. It is relaxable by another 0.001 ppm, maximum 0.002 ppm. So, except almost all phenols. So, to determine the phenols at this concentration, we will have to find out a reagent which reacts with phenol in this range. Now, one happy situation is phenols except para substituted phenols react with 4-amino antipyrine, that is the chemical reagent at pH 7.9 plus or minus 0.1, that means around pH 8, okay, in presence of ferricyanide to form antipyrine dyes. So, obviously dyes means it will have a color, and the color is monitored by the absorbance at 500 nanometers and then related to the concentration of the phenol. Now, it is a little difficult to write the structure of antipyrine complex, but antipyrine itself structure is fairly simple. That is a benzene ring here, and then a nitrogen, and then this is a ketonic group, and then this is an amino group. There is not this, this is not there. So, assume that it is not there, it is a single 5-membered ring, 1, 2, 3, 4, 5, and then there is a CH3 group here, and this is CH3 group. This is 4-amino antipyrine. So, this will react with ammonium, potassium ferricyanide. that is the basic chemical reaction to give you a red dye which will absorb at 500 nanometers. Okay. So, we go here, the typical pH is around 8, that I have already explained to you. Now, how do we go about preparing the reagents? That is very simple, and you take the stock phenol solution. Stock phenol is nothing but hydroxybenzene. That is dissolve 100 milligram of phenol in boiled and cooled deionized water, etc. All these details are available as well as I am giving you. So, you do not have to worry about how to prepare a standard solution, etc. This is all very simplified as far as users are concerned. As far as the users of my course are concerned, you just have to stick to this, otherwise one can calculate and do that. That will take some more time. I am trying to simply simplify the whole system, because this is going to be a cookbook for you, a ready reference for you to analyze whatever you would like to in drinking water. So, standard phenol solution, you just have to dilute it to 10 ppm, appropriate dilution factors you can calculate yourself, and that is 1000 to 10 means 100 times dilution. So, 100 times dilution means I can take 1 ml and dilute it to 100 ml with deionized water. And 4 amino antipyrine solution, again it is a chemical available across the shelf from chemical suppliers. We have to dissolve 2 gram of this and deionized water, but we have to remember that this solution is stable only for 1 day. That means, instead of preparing 100 ml or 50 ml and discarding it at the end of it, you can as well make very small quantities for the amount required for the day. So, you also need ammonium hydroxide solution, that is 3.5 ml of concentrated ammonium hydroxide and diluted up to 100 ml, you can get this solution, and you have to prepare a citrate buffer solution. So, this is a little tricky because citrate buffer is a complexing agent also. So, I have given you the recipe here, that is you have to dissolve 1.92 gram of citric acid in deionized water and make up to 100 ml, etc. But along with citric acid you also have to dissolve trisodium citrate as a salt. So, both of them will give you a buffer of about 6.8, and then the property of the buffer is it will not change the pH upon dilution or addition of any acid or alkali, the pH will not change. Now, you also have to prepare potassium ferricyanide. So, this is available across the shelf, that is from chemical suppliers, and potassium ferricyanide you just have to buy it and dissolve 80 gram of that, but this you can store it for in a brown bottle, but it is stable for about 1 week. See, it is important for us to remember so many chemical facts whenever you are doing environmental monitoring. For example, the stability data what I am giving, some of the reagents like this potassium ferricyanide, it is stable for 1 day. Ammonium antipyrine, that is stable for only 1 day, but potassium ferricyanide is stable for 1 week. All these things you should remember and then act accordingly whenever there is a requirement of chemical analysis or monitoring for these parameters. So, that is why I feel that it is important for me to mention the stability aspects as and when required. But if I do not mention it, it does not mean that the substances are stable for indefinite length of time. One needs to look at it from a chemical point of view and arrive at appropriate shelf life, storage, etc. Some reagents you have to store in at 25 degrees or 20 degrees, some you have to store in water, for example sample water itself must be stored in around 4° temperature. Otherwise you cannot do the chemical analysis because the results will change. So, going back to procedure, what we would like to do now is we have to prepare the standards, that is 5 ppm up to 5 ml, 10 ppm, that is 50 ppm total. I can spread it 1, 2, 3, 4, 5, that is as usual. We prepare the standard phenol solutions and then add 20 microliter. See, I am coming back to that theme of mine where I always say that 10 ml of the standard of the measurement solution is more than enough for any experiment. Especially in analytical sciences, we keep on talking about microliters, and you add 20 microliter of ammonium hydroxide solution followed by 1 ml of citrate buffer and then 20 microliter of potassium ferricyanide to each. So, you can dilute all of them to 10 ml. See, the calculation is something like this. If I take 5 ml of 5 ml of the standard phenol solution, I am going to add about 20 microliter of ammonium hydroxide and 1 ml citrate buffer, that makes it 6.2, 6.02, and then another 20 microliters of potassium ferricyanide, that makes it 6.04. So, the remaining volume is hardly 4 ml of DM water. So, whenever you want to prepare only 10 ml, it is essential that you shift to micropipettes. So, micropipettes have got a property of delivering accurate volume, but you need a little bit of experience while handling micropipettes, and the micropipette tips you can throw them once you use them, or if you are going to regularly routinely use it, you can use the same pipette also. But in biological experiments, it is better not to contaminate. Contamination becomes a very important aspect of the success of any experiment. So, in biological experiments, one prefers not to use the same micropipette tips, but in inorganic experiments you can use the same micropipette tips as long as you feel comfortable with that. So, all the reagents you are adding is going to add up to about 6.4 or 6.5 milliliters. Remaining is water. You dilute it to 10 ml, allow it to stay for about 15 minutes for the color development, and you can measure the absorbance in a spectrophotometer at a wavelength of 500 nanometer against the blank. So, again I want to emphasize a point at this juncture that you are expected to use not only micropipettes but also a spectrophotometer. It is not the colorimeter where the size of the sample is a round tube, test tube or something like that. It should be square with 1 centimeter minimum and variable if necessary required. So, this point I wanted to emphasize. So, any water monitoring body should have minimum equipments, and those equipments now I can define. What you need is a typical spectrophotometer and micropipettes, and then glassware, plastic glassware, and heating arrangement if possible, if necessary. Like that, once you have these basic minimum, this thing which involves an expenditure of about 1 to about 2 lakhs or something like that, you can monitor many of the water quality parameters in your hometown or something like that with the help of my course. So, now coming back to this determination, we have to prepare a calibration curve, and we have already said you can prepare 1 to 5 ml, that is 1 to 50 ppm of phenol, and you have to just plot it. The typical volume, recommended volume is 5 ml, that means maximum volume of your sample should be 5 ml to allow you some allowance for dilution. And then cookbook value is again this you should check on and off before you start any experiment. That corresponds to 30 microgram of phenol in 10 ml, that is 3 ppm. It should give you an absorbance of about 0.39, plus or minus 0.01. That means you can get 0.38 to 0.40 absorbance. If you get that, your reagents are good, you are good, and the experiment will be good, it will be successful. So, that is the value of the cookbook, which I have emphasized again and again. So, this is the typical curve for the phenol antipyrine reaction product. You can see that the product, the molecular absorption curve shows a very single peak. So, you do not have confusion like boron carbonic acid or something like that. So, here it is the peak very clearly defined somewhere around 500. There is not much change in the absorbance, because between 0.35 and 0.3, so we normally stick to 2 absorbance units, that is 2 decimals, especially whenever we are working with spectrophotometers, we stick to 2 decimals. Third decimal you can round it off to the nearest second decimal, and if you do that, the approximate wavelength range you can fix very easily without any confusion. Here for example, you see that in this figure the lambda max is somewhere around 510 or 520, but the absorbance value as such is not much different. So, it does not matter if you are off by 1 or 2 nanometers wavelength. Now, if we go to calibration curve, you can see how beautifully they fit into the calibration curve, and you can see that the calibration curve is linear up to 50 ppm, and analysis can be completed using very simple chemical means. As regards the interference, again we should not forget the interference. I do not have the slides for interference, but what I would like to tell you is talk about minimum interferences, that is no interference from iodide, bromide, cobalt, manganese, magnesium etc. in the 100 times level, that is 100 microgram per ml level, there will not be any interference. And the list you can get this additional list from the textbook as well as from me. I will give you some of the references, but the interferences listed here are result of our own research work. So, if you can write down these numbers, it would be fine, but it is a little tricky to show you the actual interference data, because it will extend the period of this course beyond 20 hours. So, it may not be ideal for me to give the interference data in the text, but you can always contact me, and I will be happy to provide you the interference data and any other assistance whenever you need for chemical water analysis. I hope you know my address. I am from Indian Institute of Science, retired. Now I have a analytical service laboratory. You can contact me by Gmail, mudkavi@gmail.com, MUDAKAVI. You can contact me at this address. mudakavi@gmail.com. Okay. And coming back to the interference data, which I wanted to share with you, some of them. The copper 100 ppm, it does not interfere, and then cadmium does not interfere, vanadium does not interfere. More than that, more than the non-interference, I should tell you about the interference actually. So, molybdenum, for example, molybdenum definitely interferes and it can tolerate only up to 10 ppm. Now, you can imagine that if you are determining phenol around 1 ppm or 1 ppm or molybdenum is more, then there will be definitely certain amount of interference. So, it is always like that, and up to 10 ppm molybdenum can be tolerated, and phosphate and other things. Aluminum can be tolerated up to 20 ppm, not more, because aluminum definitely will form complexes with phenol. Okay. So, that brings us to end of our discussion with respect to phenol in the drinking water. Now, let us discuss about arsenic. Arsenic is again a fantastic element, very fascinating element, widely distributed in nature, but it is not having any role in the physiology of our human beings or any living beings. That means, as of now, we have not come across any arsenic being an essential element or desirable element in the elemental spectrum. But we know that arsenic is a very industrially very important chemical, and arsenic is used in several industrial processes, paints, etc. It is very widely distributed. So, whenever you dig a bore well, it is always there are chances that arsenic may be in that. In fact, in South India, including Bangalore, Kolar, Tamil Nadu, Andhra Pradesh, etc., and in Bengal, Dhanbad, etc., arsenic is one of the main pollutant in drinking water. Till recently not many people knew about it, but nowadays we know that the arsenic concentration can exceed more than 2 microgram per milliliter, that is 2 ppm in drinking water, which is a very dangerous chemical in the environment. Now, what does arsenic do? Arsenic is a very toxic element basically. Arsenic, antimony, bismuth, tellurium, etc., they are all very toxic elements, and the property of concern is their effect on the sperm count in the mammals. Basically what happens is, if you know a little bit of biology, you will know that the male sperms and female sperms are there in every mammals, and the ratio of male to female sperms is fixed, and if this ratio is disturbed, then there will be physiological changes, and that physiological changes will be reflected in the quality of the progenies and offsprings, etc. So, arsenic is also implicated as a carcinogen. It causes cancer, and therefore, there is a huge requirement for arsenic monitoring, and the normal arsenic monitoring is approximately, the standard is 0.01 ppm, not even 1 ppm, 0.01 ppm. That means, if you want to determine arsenic, that is 0.01 means 10 nanograms, that is the detection limit. Obviously, spectrophotometer alone on its own will not be able to detect arsenic, but using special analysis technique of either converting it into a concentrate into a gas arsenic hydride and absorbing and converting it into a complex, you can give a spectrophotometric finish to the determination of arsenic and complete the determination, or one can take a larger quantity of the sample and do the analysis, bring down the concentration, bring down the volume, so that the concentration of arsenic increases. So, these aspects we have discussed just day before yesterday in the 2 classes before, where there are techniques for increasing the concentration or decreasing the concentration of the substance by extraction, evaporation, ion exchange, etc. And many of those techniques are applicable for the determination of arsenic. In fact, there are more than 100 to 150 chemical techniques for the analysis of arsenic, but what I have chosen here is, again, it is not a standard method as described by American Association of Water Examination APHA textbook, but it is a procedure developed in our laboratory and worked on by my colleague Dr. Vijay Kumar. I have adopted his method. With this method we have worked in Indian Institute of Technology, Chennai, and it is a very sensitive technique. So, the basic procedure is that the arsenic is reacted with rhodamine B, which is a dye, and it combines with molybdate and rhodamine B to form arsenomolybdate rhodamine B ion pair. It is a trivalent complex. So, the optimum complexation occurs around pH 4, the resulting in a color change from rose red to pink, and the rhodamine B I have shown you in one of my earlier samples, that is a very good triphenyl methane dye. This one I had shown you here during my explanation during fluorescence, and this is a rhodamine B available across the shelf, and you can purchase it and use it to form the arsenomolybdate complex. So, it forms a pink complex with lambda max around 595 nanometers, and the absorbance is proportional to the concentration of the arsenic. So, sometimes you will come across not arsenic element, but quite often you will come across arsenic as arsenate as an anion, but also arsenite also. So, if there is a possibility that arsenate will react, but arsenite will not be able to react, but you will have to oxidize it to arsenate and then carry out the reaction as usual. So, it requires an additional step in the application of molecular spectroscopy to the determination of arsenic. So, what we have to prepare? The reagents are arsenic solution 100 ppm, that is our stock solution, and you have to dissolve approximately 41.7 milligram. I am going to give you only like this because my interest is environmental should not be polluted by the laboratory chemicals also. So, use minimum quantity and minimum volume. So, you have to dissolve arsenate, disodium hydrogen arsenate available across the shelf and make up to 100 ml. Standard is always 1 ppm you can prepare. You can dilute 1 ml of the stock solution to 100 ml, and ammonium molybdate we have to prepare. Again I have given you the procedure here by dissolving 2 gram of ammonium molybdate tetrahydrate in deionized water. Rhodamine B solution is available across the shelf. It is a very prominent organic dye used in nail polish and several other components, cosmetic chemical also, and it is also used in in river water monitoring, which I had explained to you during fluorescence method. And rhodamine B structure, it is a triphenyl methane dye. I can give you the structure of rhodamine B. Typical structure is like this. These are all aromatic rings. Not here, but here, this is not there. And then this is nitrogen group, CH3, there is one more benzene group. These are known as triphenyl methane dye. There are 3 benzene rings. Again there is nitrogen, CH3. This is rhodamine B. The structure is 9,2-carboxy phenyl, that is the chemical name, 6-diethylamino, three xanthine diethyl ammonium chloride. Diethyl ammonium This is a very famous dye, especially used in textiles also. Many of the pink dresses, whatever you are, if you are wearing, chances are that it will contain rhodamine B dye, and it is also a good chemical reagent, and one can use this as an analytical reagent also. So, these are the typical reagents we have to prepare, and we also have to carry out the reaction around pH 4. So, the best way to carry out a pH 4 reaction is to use sodium acetate acetic acid buffer. So, for this recipes are available across all textbooks, and I have also given you the numbers here, and we have to adjust because normal sodium acetate acetic acid buffer has a pH of about 4.76. So, you have to adjust the pH to 4 because the reaction is best carried out around pH 4. So, if you prepare a sodium acetate acetic acid buffer, you have to add acid, hydrochloric acid, until you bring it to pH 4. So, this is phenyl polyvinyl alcohol. This is a reagent which is used as a stabilizing agent for the triphenyl methane dye complex to remain in solution. In the original method developed by my colleague Dr. Vijay Kumar, he had extracted the complex into benzene and then completed the analysis. We have worked further on this method to show that the addition of polyvinyl alcohol stabilizes the color in aqueous medium itself. One of the endeavors of ours to bring you this course is to keep the procedure simple, and then less quantity should be less, and it should be very easy to procure the chemicals for you from the suppliers, and it should be it should not be time consuming for the chemical analysis. So, if proceeding to the procedure, what we would like to tell you is you have to take 0.1 to 2.5 ml of the standard arsenic solution, that corresponds to how much? The working ppm is 1 ppm. So, if you take 2.5 ml, you will be taking 2.5 microgram of the standard arsenic solution. So, that is the highest limit, high end limit. So, in remaining things are all very simple. Add ammonium molybdate, 2 ml of acetate buffer, 6 ml of deionized water and mix by swirling. Add 1 ml of rhodamine B followed by 1 ml of polyvinyl alcohol solution. This polyvinyl alcohol is also available across the chemical suppliers, across the shelf. You can buy it and you just have to prepare it fresh daily. So, then you have to make up to the mark and measure the absorbance at 595 nanometer, but you can also prepare a calibration curve of absorbance versus concentration by referring to the sample. You can determine the actual concentrations. So, the recommended sample volume is 5 ml, that is the maximum, that is 5 ppm, and cookbook value, if you take 0.5 microgram, that is of arsenic in 10 ml, that is 0.5 ppm, it should give you an absorbance of about 0.161. So, going back to this, the recommended drinking water concentration is 0.01 ppm, right. So, for 0.01 ppm, you should get 0.03 absorbance. So, your sample volume, if it contains 5 ml, 5 into 0.1 is 0.5 ppm. So, 0.5 microgram should give you 0.161, that corresponds to the drinking water analysis as prescribed by the pollution control board, state as well as central pollution control boards. So, this is a modified method of arsenic determination for you, and we are very happy to bring you this method. The actual spectrum I am showing you here. The lambda max, you can see there is only one single peak, you do not have much choice, and it is a very simple method that permits you to determine arsenic in different concentrations at this level. So, this is the calibration curve. You can see that whenever we are working at very near detection limits, the spread of the points is a little more, but as I have already explained to you earlier, plus or minus 10% should be acceptable in spectrophotometry, and that is what has happened here. I have drawn a linear curve here. The linearity curve is given by y is equal to 2.85x plus or minus 0.018. There is a certain amount of non-zero origination, but R square value is approximately very good, that is the reliability is 0.974. So, we will stop our discussion on this and continue our discussion on other parameters in the next class. Thank you very much.